This is the 7th lecture on DSP, and we propose to discuss FIR and IIR types, recursive and non-recursive realizations, and we wish to gain an entry to the frequency domain. In the last lecture, we had reviewed the trick for convolution that I had talked to you about in lecture 5th. Then we said it can be done also by polynomial multiplication, and we saw that the results are the same, they have to be the same, otherwise it is not valid. We discussed what is an inverse system and we gave an example of an inverse system. Then we also mentioned that parallel interconnection adds up the impulse responses, and it is very important in practice because parallel processing speeds up the processing. So, for fast DSP you have to use parallel decomposition. Then we talked about stability in terms of h of n, and we said that a system is stable if the impulse response is absolutely summable. The limits are of course from n equal to minus infinity to plus infinity. And we ended up in discussing difference equations, which are very similar to differential equations of continuous time domain. And then we said that the solution to a difference equation consists of two parts, the complementary part and the particular solution part. And we also made a strong point about the common mistake that people do to evaluate the constants of the solution. The constants should be evaluated only after adding the particular solution. The particular solution is of the same form as that of the excitation, except for cases where the excitation also contains an eigenvalue of the system. The eigenvalues are the roots of the characteristic equation or the zeros of the characteristic polynomial. We discussed the case of distinct roots, we discussed the case of repeated roots, and then we took an example of the excitation containing one of the eigenvalues. There is another method that is followed in practice, particularly in systems engineering, because it has physical interpretations of solving a difference equation as the sum of the total solution for a difference equation. One way is to view it as a sum of complementary function and the particular solution. The other way is to view it as a problem of superposition. The response of a system depends on the input as well as the initial conditions. Initial conditions are also known as initial states. Initial conditions are also known as initial states of the system. That is, if you specify initial conditions, then you know what parameters the system has before the excitation has been applied, and therefore the superposition principle says that if it is a linear system, then the response would be due to each excitation applied separately, and then you add up all of them. Now, the excitation in a difference equation or a system, a digital system, consists of two parts, namely the input x of n and the initial states, and therefore the output response excuse me, y of n shall be the sum of two components 0 input of n plus the component due to 0 states, 0 state system. This is another way of looking at the complete solution. However, the 0 input condition is not the same as the complementary function. There is a difference. 0 state condition is not the same as the particular solution. One has to distinguish between the two. The 0 input condition, I want you to follow this carefully, and then I will tell you which procedure I prefer. 0 input condition is the solution to the equation with x of n equal to 0. Therefore, the form of the solution shall be the same as the form of the complementary function. The difference is that the complementary function now shall be totally determined from the initial conditions. In our previous procedure, I warned you that initial conditions have to be revoked only after adding the complementary function to the particular solution. In this procedure, the 0 input condition is the output with x of n equal to 0 and the constants determined from the initial conditions. Naturally, this will be different from the complementary function. Okay? Whereas 0 state condition says that the initial conditions are 0, and therefore, you find the solution to the equation. Again, the solution will consist of a complementary part and a particular solution, okay? And then evaluate the constants by putting initial conditions equal to 0. Is the procedure clear? Y z I of n is simply the complementary function with constants determined from the initial conditions. Y z s of n is the solution, total solution to the equation, that is complementary function plus particular solution with constants determined from 0 initial conditions. Okay? So, these are two different procedures for finding the solution to a difference equation. This is what the system theorists prefer, because 0 state condition and 0 input conditions both are realizable in practice, and in an experimental situation this is to be preferred. As far as theoretical computation is concerned, I prefer the previous procedure, because this is a repetition of the same procedure. You have to evaluate the constants twice, whereas the former procedure the constants are evaluated only once. But you should understand what we mean by 0 state and what we mean by 0 input condition. Okay? And you take any of the examples that we did last time and you work out according to this, the solution, the ultimate solution has to be the same. It has to be the same, there is no other alternative. But as far as computation or calculation on paper is concerned, we prefer the previous procedure, because the constants have to be determined only once. Okay? As an example of 0 state response, you know that if I feed to a digital system an impulse function delta n, digital system which is characterized as linear, time invariant and causal, linear, time invariant and causal, then what is the characteristic? H of n should be equal to 0 for n less than 0, agreed? Which means that H of n is the 0 state response of the system, isn't that correct? H of n is 0 for n less than 0, it means that it is initially relaxed, there are no initial conditions. h of n is defined like that. To find out h of n, you must first reduce the system to one with 0 initial state. All initial conditions are made equal to 0. So, we say h of n, let me write it down, h of n is the 0 state response of an LTIC DS, linear time invariant causal digital system. Okay? H of n is an example of 0 state response. Once this interpretation of h of n is obtained, then h of n can also be written, h of n is the total solution of the system to an input equal to delta n with initial states equal to 0, and therefore, the form of h of n shall be alpha I lambda I to the power n summation n equal to 1. If it is a capital nth order system, then summation n equal to 1 to capital N. Agreed? It shall be of the same form as the complementary function. Why? Because delta n is 0 for n greater than 0. Agreed? Now, so stability demands that summation absolute value of h of n should be less than infinity. That is what defines a stability, a stable system. If this summation is to be less than infinity, then what is the condition on these eigenvalues? Obviously, summation h of n, I am not writing the, it is n equal to minus infinity to plus infinity. Okay? Summation h of n would be the summation of this sum, okay, and therefore it would be less than summation n equal to 1 to capital N magnitude alpha I magnitude lambda I to the power n. Agreed? If we take the magnitudes, obviously it would be less than or equal to. Now, alpha i's, magnitude of alpha i's should obviously be finite, right? If alpha i's are not finite, then your system to start with is unstable. Okay? So, alpha i's are finite, and therefore, lambda I to the n summation should be less than infinity. How can you guarantee this? Therefore, lambda I, if this is less than infinity, magnitude lambda I must be less than 1 for all I. Okay? So, lambda I equal to 2, which we got earlier, is an unstable system. We took a first order system where the eigenvalue was equal to, no, it was minus 0.5. Isn't that right? That was a stable system. But if one of the roots of the characteristic equation magnitude exceeds unity, it can be complex. If the magnitude exceeds unity, then you know the system is unstable. As you shall see later, these eigenvalues are also the poles of the system in a complex plane. So, the poles should be confined to a unit, to be within a unit circle. We shall come to this later after we introduce the Z transform, but right at this stage in the totally working in the time domain, you know that the roots of the characteristic equation must be such that they are bounded in magnitude by unity. Even lambda I equal to 1 is not permitted because it is marginally stable. and we cannot work with a marginally stable system, because you never know, due to small perturbations it may go wild or insane. We then introduce the terms FIR and IIR. A very simple. Finite impulse response and infinite impulse response refer to the length of the impulse response. If a system has an h of n which is non-zero for n1 less than equal to n less than equal to n2 and 0 everywhere else, that is, our range of vision in the on the n axis is limited, is finite, then we say it is a finite impulse response system. In a finite impulse response or FIR system, the output, if you write the convolution, would be given by, what is the convolution? Xk h of n minus k, we are talking of a linear time invariant system, k shall go from n1 to n2. So, the limits are finite and there are only n2 minus n1 plus 1 number of samples in the impulse response. On the other hand, if n1 or n2 or both go to infinity, then the system becomes IIR. Agreed? If the length of the impulse response is infinite, it is an infinite impulse response system. The accumulator 1 by m, no, the moving average system, y of n is equal to 1 by m x of n minus k, k equal to 0 to m minus 1 is an FIR system. Agree? What is its h of n? What is this sequence h of n?
So 1 by m minus n minus summation of
1 by m
summation of k is equal to 0 m minus 1 divided n minus k.
Yes, but what are the samples in the sequence h of n? What are the samples? Delta n minus k is 1 for k equal to 0, all right. For k equal to 1 it is also 1, and therefore 1 by m and so on, the last one is also 1 by m. This is n equal to 0 and this is n equal to capital N. Agreed? So, all samples are equal. It is a rectangular gate u of n minus u of small n minus capital.
n plus 1.
I have made a mistake here. Have I or have I not? Pardon me?
n equal to m. n equal to m.
M or m minus 1?
n.
The upper limit is m minus 1, so it has to be m minus 1. The length is capital M. Okay. Now, if I whether it is FIR or IIR, the output can always be written as a convolution. That is, it can always be written as xk h of n minus k, whether it is FIR or IIR. The limits shall depend on the nature of xk and hk. For example, if xk is causal and so is hk, if the system is causal and the input is also causal, then k goes from 0 to small n. Agreed? Now, in the computation of this, whether it is FIR or IIR, we are only using the present values of the input and the past values of the input. Okay? We are not using any past value of the output. Agreed? And therefore, this computation is non-recursive. This shows that FIR filters can be computed non-recursively. IIR filters can also be computed non-recursively, although in general IIR filters are more convenient to compute recursively. In other words, I wish to emphasize, I think I made this point earlier also, that FIR, did I or I didn't? In the many textbooks, these two terms are used interchangeably, which is a gross mistake. FIR is not necessarily non-recursive and IIR is not necessarily recursive. Recursive and non-recursive, the two terms are used to describe the process of computation, whether you require feedback or you don't require feedback. All right. Recursive computation requires feedback, non-recursive does not require feedback. And as I have shown you, this convolution operation does not make a distinction between FIR and IIR. Therefore, IIR filters can also be computed non-recursively, although in general it is more convenient to compute it recursively. Okay. I have shown examples of recursive computations earlier. Let us take, what about a FIR filter to be computed recursively? Have I shown that example? No, I have not. Let us take an FIR. Y of n is equal to x of n plus x of n minus 1. Well, obviously the computation is non-recursive, but I can also write y of n minus 1 as equal to x of n minus 1 plus x of n minus 2. And who prevents me from writing y of n minus y of n minus 1 as equal to x of n minus x of n minus 2? That is, y of n is equal to y of n minus 1 plus x of n minus x of n minus 2. And this is a recursive computation. I require the present value of the input, the last but 2 input sample and the last output sample. Therefore, it is a computation with feedback. All right. Therefore, FIR filters, I repeat, FIR filters can be computed recursively or non-recursively. IIR filters also can be computed either recursively or non-recursively. The two terms should not be confused with each other, and if an SCDR student does that, it brings discredit to SCDR. So, I am worried. Okay, you must not make this mistake. Many textbooks make this mistake. We take an example now. We take an example of an integrator, a digital integrator. What is an analog integrator? Analog integrator is y of t is equal to integral 0 to t x tau d tau. Okay. This is analog integrator. There should be some lower limit. Well, let us put it at 0. We assume that xt is causal. Okay. Now, if I wish to do it in the sample domain, well, we can write as y of nt, that is at the instant nt, as equal to y of n minus 1 t, okay, at the previous instant, plus integral n minus 1 t to nt x tau d tau. This is exact. This is the exact equation. I have integrated up to n minus 1 times capital T. Then I have integrated between this interval n minus 1 t to n t. This is exact. All right. Now, I can approximate this because x of n in a digital domain, x of t is known only at n minus 1 t and n t. I do not know the value in between. It is not defined for a digital signal. Therefore, I can approximate this as y of n minus 1 t plus, let us take the average value between the two, half of x of n minus 1 t plus x of n t, and then multiply by the interval. Okay. This is how integration is carried out by a digital computer. A digital computer handles only digital numbers. Okay. This is called a numerical approximation procedure. There are many algorithms for numerical integration. This is one of them, perhaps the simplest. You just take the average value and then multiply by the interval. Now, if I translate this in the digital domain, well, this is what I shall write is y of n t, I shall write as y of n would be equal to y of n minus 1 t, I will drop capital T, y of n minus 1 plus capital T by 2, the interval must be known, multiplied by x of n plus x of n minus 1. Okay. Let me write it again, y of n equals to y of n minus 1 plus capital T by 2 x of n plus x of n minus 1. From this equation, can you guess whether it is an FIR or an IIR system? It is not obvious. Only thing I know that is being computed recursively, because I require a yn minus 1. Incidentally, this is what forms the basis of the so called bilinear transformation, which we shall discuss at a later date. But let us focus on this. Let us assume that the system is causal. Causal means h of n is equal to 0 for n less than 0. Okay. If it is causal, then h of n would be h of n minus 1, after h of n is the response to delta n, okay, plus capital T by 2 delta n plus delta n minus 1. So, let us compute h of negative argument is 0. So, we start computing at from h of 0, n equal to 0. H of minus 1 is 0, delta n at n equal to 0 is 1. So, it is simply capital T by 2, agreed. Delta minus 1 is 0. What is h of 1? H of 1 would be h of 0 plus capital T by 2 multiplied by delta of 1 is 0, delta of 0 is 1. So, it is simply T by 2, which means that this is equal to capital T, agreed. H of 2 is equal to h of 1 plus this term does not contribute anything beyond n equal to 1, and therefore, it is simply equal to capital T, and this continues. H of n is equal to capital T for all n greater than equal to 2, and it does not terminate anywhere. You can go to infinity, and therefore, the impulse response is of infinite length, and the impulse response, if I draw it here, it would be capital T by 2 at n equal to 0, at n equal to 1 it is capital T, n equal to 2 capital T, and this goes on. And if you so desire, you can write this as capital T by 2 delta n. I want to express in terms of delta and u, and plus capital T times u of n minus 1. Wonderful. Is there some other way I can express this?
un minus del T TUN
TUN, wonderful,
by 2 del n.
minus T by 2 delta n. This is perfectly correct. Okay. There are many ways of expressing the same result. Whichever looks nice, you take that. So, this is an infinite impulse response system, and recursion and non-recursion have nothing to do with the length of the impulse response. Okay. Any length of impulse response can be computed recursively as well as non-recursively. Now, it is time to enter into the frequency domain. Frequency domain representation of digital signals. In the analog domain, continuous time domain, there are various kinds of transforms which takes small t, the time variable, to the frequency variable. It can be omega if it is Fourier transform, or small s, the complex variable, if it is Laplace transform. All right. In the digital signal domain, the Fourier transform is the most important transform, and the corresponding transform of Laplace is the so called Z transform. Okay. We shall talk about both, but it is important to recognize that the Fourier transform, one terminology, most of the textbooks write this as discrete time Fourier transform. I find this pretty confusing because we shall also introduce what is DFT. So, DTFT and DFT, they are very close to each other. So, discrete time Fourier transform I shall simply call Fourier transform. Okay. The textbook uses DTFT, but we will keep things simple by calling this as Fourier transform. DFT is something else we shall define at a later date. The Fourier transform of an analog signal x of t, as you know, is capital X of j omega, which is the integral from minus infinity to plus infinity x of t e to the power minus j omega t dt. Well, we should slightly modify this because small omega is a symbol we have reserved for normalized digital frequency. So, we will say capital omega, okay, x of t e to the power minus j capital omega t dt. This involves an integration. In the digital signal domain, the Fourier transform of a sequence x of n is very simply defined as a summation of x of n, then e to the power minus j. There is no concept of small t there, it is only a number n. So, n times the normalized digital frequency omega, where n goes from, in general, from minus infinity to plus infinity. This is the definition of Fourier transform, and because it is a polynomial in e to the power j omega, it is a polynomial in actually in e to the power minus j omega. Because it is a polynomial, the symbol that is used for it x of e to the j omega, not x of j omega. Okay. There is a difference in the symbolism. Let me write this again. Capital X of e to the j omega is equal to summation n equal to minus infinity to plus infinity x of n e to the power j n omega. So, it is a much simpler definition. In general, this is a complex quantity because e to the power j omega is cosine omega plus j sine omega. Therefore, I can write this as a real part plus j times an imaginary part. Both real part and imaginary part are real quantities. Isn't that right? they are imaginary quantity. You have to multiply by j to make it imaginary. Okay. So, I am not writing the argument would be e to the j omega, similarly e to the j omega. Okay. So, if you want to find the imaginary part of a signal, you have to multiply a real quantity x j e to the power j omega by j. All right. So, it can also be written in terms of a magnitude and phase, that is, you can write this as capital X of e to the j omega magnitude, it is a complex quantity, then e to the power j some angle of x. All right. Let us write this as capital M of omega e to the power j theta omega. If you look at the definition carefully, the definition says that capital X of e to the j omega is a continuous function of omega. Although my x of n is discrete signal, it exists only at n equal to 0, plus minus 1, plus minus 2. In the frequency domain, it is a continuous function of omega. It also shows that if omega is incremented or decreased by twice pi or any multiple of twice pi, the function does not change, because e to the power j omega is the same as e to the power j omega plus minus 2 pi k, and therefore capital X of e to the j omega is a periodic function of period 2 pi, and this strengthens our statement, earlier statement, that our range of vision is from minus pi to plus pi. We do not have to go beyond that because it is periodic. The other thing that one should remember is that the real part, in the real part, if omega is changed to minus omega, the real part does not change. It is an even function of omega, because the magnitude is even and cosine of theta is an even function. The real part is nothing but magnitude m multiplied by cosine theta omega. Therefore, the magnitude is even. The phase must be odd. If you change omega to minus omega, the sign of the phase changes. Okay. The magnitude and the real part are even functions. The imaginary part and the phase, they are odd functions of omega. All right. One also notices that if theta is also periodic with a period of twice pi, agreed. Now, if theta is incremented by twice pi, neither cosine changes nor sine changes, and therefore, while m omega can be found uniquely, there will exist a fuzziness or an uncertainty about the actual value of theta. If you find theta equal to minus 45, it could be 360 minus 45 or 720 minus 45 or minus 360 minus 45. Cosine and sine shall make no change, and therefore, about phase there is an uncertainty. We remove this uncertainty. We cannot work with uncertainty in a laboratory, in a hardware. Therefore, we decide once for all that we shall only consider the principal value. Principal value is the value which lies between minus pi and plus pi. Okay. Why does one go to the frequency domain at all? Frequency domain is complex. There is a real part, there is an imaginary part. Why does one complicate life? Because it simplifies life in some other fashion. Processing of a signal, viewing processing in the time domain is much more complicated than processing in the frequency domain. For example, convolution, which requires a multiplication of two signals, then summation is simply replaced by multiplication in the frequency domain. You do not have to do this graphical business and all that. Okay. So, one goes to the frequency domain, one intentionally complicates life to be able to simplify in some other fashion. Design, analysis, synthesis, everything is much simpler in the frequency domain than in the time domain. We take an example of Fourier transform. The simplest example is x of n equal to delta n, an impulse function. Then you know capital X of e to the j omega, which by definition is delta n e to the minus j n omega, n equal to minus infinity to plus infinity. Now, delta n exists at n equal to 0 only, and therefore, the summation shall be replaced by a single term, and that is equal to 1. When n equal to 0, e to the minus j omega is n omega is identically equal to 1. So, delta n therefore, the Fourier transform is 1. Now, you notice a symbol that I have introduced here, a double sided arrow. It means that the Fourier transform is unique. In other words, if the Fourier transform is given, you should be able to go back to the time domain uniquely. There should be no arbitrariness, no confusion, no uncertainty. It must be a one-to-one representation, otherwise it is invalid. And this is why we insisted that phase should be viewed only in the principal domain. Otherwise, there is uncertainty. We cannot work with uncertainty. Let us take the second example. X of n is equal to half to the power n u of n. If you take the Fourier transform, capital X of e to the j omega is n equal to, since it is u of n 0 to infinity, half to the power n e to the power minus j omega n, which I can write as summation, limits I am not writing, e to the power minus j omega by 2 whole to the power n, while n equal to 0 to infinity. Does this summation converge? If it does not, if it diverges, then the Fourier transform does not exist. The existence is guaranteed here because the magnitude of e to the minus j omega is 1 and half to the power n, and as n goes to infinity is 0, and the sum is a finite number. The sum is 1 by 1 minus half e to the minus j omega. All right. So, the Fourier transform does exist, and this is the value. Capital X of e to the j omega is equal to 1 by 1 minus half e to the power minus j omega. I can write this, I can find the magnitude and phase of this function. I can write this as 2 divided by 2 minus cosine omega, then plus j sine omega. So, the magnitude I can write as 2 divided by magnitude of the numerator divided by magnitude of the denominator, and the magnitude of the denominator would be 4 plus 1 5 minus 4 cosine omega. Is this obvious? 2 minus cosine omega whole squared plus sine squared omega, and cosine square plus sine square makes 1. So, 4 plus 1 is 5, and the twice AB term is 2 multiplied by 2 multiplied by cosine omega. So, 4 cosine omega, and the phase is equal to the phase of the numerator, which is 0, then minus the phase of the denominator, which is tan inverse of imaginary part, that is sine omega divided by 2 minus cosine omega. If you look at these expressions carefully, capital X magnitude obviously is maximum when cosine omega is 1, isn't that right? You want the denominator to be as small as possible. So, the maximum occurs at omega equal to 0, max capital X magnitude at omega equal to 0, and what is the value? 2. What is the minimum? Omega equal to plus minus pi, then it would be 5 plus 4, 9, so it would be 2 by 3. So, the magnitude I know varies between 2 and 0.666 ad infinitum. It is a recurring number. The phase, what can you say about the phase? What is the phase at omega equal to 0? It is 0 because this is a real quantity. Okay. So, the phase starts from 0 at omega equal to 0, and I have got here a plot of the magnitude and phase of this quantity 1 by 1 minus 0.5 e to the j omega. This picture is worth 1000 words if not more. Look at the picture. I have highlighted this with color. The magnitude is periodic, it is obvious, and the range of vision is this red marked region minus pi to plus pi. In fact, if we plot from 0 to pi, this is good enough, because minus pi to 0, it is an even function, and therefore I can construct the latter. So, we shall basically confine to 0 to pi, and if you look at 0 to pi range, what can you say about the function of this signal? The signal is reach, pardon me? Monotonically decreasing, agreed, but the function, the signal x of n, half to the power n un, is reach in low frequencies. Is that right? 0 frequency is maximum, then it gradually goes down. So, it is a low pass signal, agreed? Okay. The phase on the other hand is odd, which is obvious. The phase at this frequency is the negative of the phase here. The phase is an odd function. It is not sinusoidal, it is a slanted sinusoid. It can be of any arbitrary shape, but there is a maximum, there is a minimum. Again, in phase we confine to minus pi to plus pi, and since we know phase is an odd function of frequency, we simply plot from 0 to pi, agreed, and we remove all uncertainties by confining the phase value also between pi and minus pi. Fortunately, here the maximum does not go beyond 0.5 radians. What is pi? 3.14. So, between plus 0.5 and minus 0.5 radians. This picture, as I said, is worth 1000 words. Now, we come back to the definition of Fourier transform, that is capital X of e to the j omega equal to summation x of n e to the power minus j omega n equal to minus infinity to plus infinity. I have already made the point that if the Fourier transform is to be of any use, then it must be unique. It must be unique and one to one, that is, given x of n, you should be able to find capital X of e to the j omega. There cannot be two answers. If there are two answers, one will get full marks, the other will get 0. You understand? One will be right, the other will be wrong. Both may be wrong, that is also possible. Both may be wrong, but if one can arrive at the correct answer, that answer is unique. It cannot be expressed in any other form. In a similar manner, if the signal is given in the frequency domain capital X, you should be able to go back to x of n. You should be able to go back to the time domain. And if you look at this function, and you recall what Fourier series was, isn't it exactly the Fourier series, not of the time function, but of the frequency domain function? It is periodic of period pi, and it is expressed as a sum of exponentials with coefficients x of n. Therefore, x of n must be given by the formula for evaluation of Fourier coefficients, that is 1 over 2 pi integral over one period. What is the period? Minus pi to plus pi, capital X of e to the j omega, then multiplied by an exponential with a positive sign e to the j omega n and integrated over omega. So, this is the inverse Fourier transform relationship. Okay. Now, the two are not independent of each other. This is another point I want to make very clearly and very loudly. The two are not independent of each other because we require one to one transformation. In other words, if this is given, this can be derived. If this is given, then this can be derived. So, both are not matters of definition, only one of them can be defined, the other should follow. In other words, if I start from here, I should be able to derive this, okay? And the derivation is extremely simple. What you do is substitute for this from this relation and then evaluate. You will get an integral of the form minus pi to pi e to the power j omega n minus m d omega. The trick is that you cannot retain n here and n here. Do you understand this? If you substitute for capital X of e to the j omega, you cannot retain small n because the summation and the integration are independent of each other. The integration contains j omega n, so you must change this dummy variable to m, then minus m. And as you know, this function consists of cosine and sine. So, over one period the cosine will become 0, integral sine will also become 0, except in the case n is equal to m. In other words, if this is 1, then 1 d omega, the integral will be twice pi, and there is a twice pi here, and that is the way you prove that the right hand side is equal to the left hand side equal to x of n. The derivation is simple. I have explained in words, it is given in the book. You try to follow that. I repeat in conclusion that recursive is not necessarily IIR, non-recursive is not necessarily FIR, and vice versa. And in Fourier transforms, why do you go to Fourier transform? To make life more complex, because analysis, design, synthesis become much simpler in the frequency domain. But in frequency domain has to be handled with care because of uncertainty in theta, the phase. There is no uncertainty in magnitude, but theta can be multi-valued because addition or subtraction of twice pi does not matter. The third point that I make is that in the Fourier transform relationship, Fourier transform and inverse Fourier transform are not independent of each other. One depends on the other. It has to be so for it to be useful to us, to any engineer. It has to be, if it has to be useful, then the transformation must be unique. That is, given one, you can find the other. All right. So, one is a matter of definition, the forward transform or the reverse transform. How did I find IFT? By comparison to Fourier series. That was also somewhat unconventional, because Fourier series usually is written as a periodic function in time equal to summation of exponentials. Now, here we wrote a periodic function in frequency. That is how the definition is. So, it was not difficult for us to find out what the inverse Fourier transform is. we shall look into more details next time.